A long time ago. All right.
And you can also see the tab on the card.
Yeah, okay, great. So I'm going to talk about a new data set that we produced from VIIRS. And it is detecting waste heat at about 20,000 sites worldwide. And so this is about lights at night. And so there are various types of lights, and you need different wavelengths to record these. There are things such as cities, there are boats out in the water, there are industrial sites, there are fires and flares, and oftentimes all these lights are mixed in together. And so part of what we do is filter and try to assign each of the features to a category. And we use various evidence lines to do that, one of which is temperature. And we work with data from VIIRS, which is a meteorological sensor. It's in a polar orbit, has a 3,000 kilometer swath width. And the daytime imagery looks like this. I think we saw some imagery like this in the first session. And so it's beautiful for looking at weather and the land surface and the ocean. But at night, it does something that we call low light imaging. And the most widely known of the low light imaging spectral bands on VIIRS is the day-night band, which straddles the visible and near infrared. And it collects low light imaging data to meet a requirement from the meteorologists who said they wanted to be able to see clouds at night in the visible to go along with the thermal. And so this traces back to the 1970s when the meteorologists were first beginning to use satellite data, and their favorite pair of bands, originally the only two that they had, was the long wave thermal and the visible. And they could, that worked quite well during the day. They had sensors that could do that. But at night, the visible channel couldn't see anything. And so they asked the engineers, can you develop a sensor that could see clouds at night? And the solution was to use moonlight as the energy source, because moonlight is 400,000 times dimmer than sunlight. You needed light intensification. And so we have this capability on VIIRS. We had it previously on DMSP, which is an Air Force meteorological sensor, where it's much cruder than VIIRS. And so I always have to say thanks to the meteorologists for getting us this capability. But there are 4 other channels on VIIRS that collect a type of low light imaging data. And so VIIRS, the day-night band, uses light intensification to achieve low light imaging at night. But there are 4 channels on VIIRS, 2 in the near infrared and 2 in the shortwave infrared, that are daytime channels. And so their detection limits are set based on the reflectivity of dark surfaces lit by sunlight, that they wanted to be able to record those brightness levels, even though it's very dark. And so that's the lower detection limit. And then an upper detection limit is where the sensor saturates, is where they wanted to be able to have everything on scale, even for bright surfaces of cloud tops or sand dunes, whatever it might be. So these 4 spectral bands, they're daytime channels that continue to collect at night. And that's really unusual, because most sensors that have these spectral bands, and a lot do, they don't record at night. The instrument's still running, but they just don't bring the data down. And if you ask the operators, why don't they bring that data down? They say, well, there's nothing to see. To which I quip that, well, there's almost nothing to see. And so this is an example of a fire in California. And you can actually see the outer perimeter of the fire. And you see it very clearly in the near infrared and shortwave infrared, because there's no sunlight. And so the instrument is recording the noise floor of the sensor, and that's punctuated by these strong infrared emissions from fires and other things, other objects. You can still see it, that those features in the midwave infrared, but they're obscure because they're mixed in with the radiant emissions of the Earth itself at that wavelength. And as you go to longer and longer wavelengths, those fire features begin to disappear because you're getting off towards the edge, the long wavelength edge of their Planck curves. So this is the data source that we use to make a product called Veer's Night Fire. And so we run through about 300 gigabytes of nighttime Veer's data every 24 hours, and we run algorithms to look for infrared emitters in those 4 short wavelength channels, and then the mid-wave infrared as well. And sometimes we get asked, well, why do you have a multispectral fire product? NASA's fire product just uses 2 spectral bands, one here and one here. And so the reason we use so many channels is that we're interested to get the Planck curves. And so we get the detections, and then we do what we call dual Planck curve fitting, one Planck curve for the background and one for the infrared emitter. And that's how we apportion the radiant emissions in the midwave infrared, where you've got a mixture of contributions from the background and the infrared emitter itself. We get lucky with these 4 channels because it's all from but yet the emitter, there's no background. But with the Planck curve, then we can calculate the temperature using Wien's displacements law. We can, knowing the size of the pixel footprint and the amplitude of this Planck curve, we can calculate the source size. And then temperature and source size are inputs into the Stefan-Boltzmann's law that we use to calculate the heat output. And so we do that for every night, and then we can assemble that data and take a look at it. And so here's a month's worth of data. This is temperature versus source area. And so this is the actual data from our algorithm. And you can see there it's bimodal. There's a hot group and a cooler group. And this hot group is gas flares. And in this cooler group, it's dominated by biomass burning, but there is also some industrial sites in there. And so part of our challenge to make this map of waste heat from industrial processes is to tease apart the biomass burning from the fixed position infrared emitters. Now, the other lines on here are the detection limits for this various spectral bands. And so this one right here, this is in the midwave infrared. And that's the traditional fire detection band. And you can see we're detecting a lot of pixels that are below that detection limit. And so they're being picked up by shorter wavelength channels. This gold line is the 2.2 spectral band, and this red line is 1.65 microns. And so to calculate the temperature, you need to have detection in at least 2 spectral bands. And so that's why there's a gap here where you only have detection in 1 spectral band. Interestingly, here's the day-night band detection limit line. And so above 1000 K, it has the lowest detection limits for infrared emitters of any of the Veer's spectral bands. Okay, so then we make these composites that have all the detections, and we begin to filter out the biomass burning, and we find the areas that have persistent infrared emitters. And then we switch over to this analysis where we look at the actual, from the Veers, we get the position of the pixel center for each detection in latitude and longitude. And we can make that into an image. And if there's a single emitter, we get a little square, which is actually a projection of a Veer's pixel that would cover an emitter that is somewhere inside that square. And so that's how we recognize a single emitter. For sites that have multiple emitters, we get something like this. But what we do is we generate these and then we divide them up into, and we generate vectors that surround each emitter. And so over here, there's only a single vector around this feature, but here we have to split this up. And so then we can track that individual emitter through time. And so this is actually what I was going to show you on Google Earth, but I'll show it to you here. This is our new map of infrared emitters. It's global, and there's about 20,000 sites. And we've got preliminary labels. So industrial sites are these red features. Steel mills are these crowbars or monkey wrenches. Refineries are little gas pumps. And flares are these red bubbles, red balloons. And so, landfills are the white triangles. And so for any one of these, you can take a look at the temporal profile. Let's see, here's our catalog as it stands now. So I've got more than 20,000 sites. 13,000 of them are upstream gas flares. Those are in production areas. About 10% of that number are downstream. Those are in refineries, 1494. Then we've got gas flares at coal mines where methane is coming out and they want to dispose of it. And then there are some landfills that also have gas flares. We found 1563 infrared emitters at steel mills. And it turns out that often steel mills, they're so large and complex, there are several emitters in a single site. So this is 1563 individual sites. It's actually for individual emitters. Industrial sites, we still haven't really broken that down, but there's quite a few of them, and then a few cement factories, wood industries, volcanoes, and some that we haven't gotten labeled yet. All right, so this is actually a site from not far from here. This is in Michigan at a place called Zug Island, and it is a steel mill, and these are our temporal profiles. And so on the top panel, we have the radiance in the shortwave infrared at 1.6 microns. And then in the middle, we've got the temperature. And so this site looks like it had a temperature of about 1300 for quite a long time. And then it appears that for some reason that the temperature went up. And down here, this ticker tape records the cloud situation when there is no detection. And so it's blue if there is no detection and it's clear, and it's red if it has no detection and it's cloudy. And then this other little ticker tape here is for the detections that have only a single band, so we can't calculate the temperature. And then down here we have radiant heat. And this is actually an example of a site that had a decrease in activity during the COVID period. And so you can see it drop in the middle of 2020 into 2021. There's this dip that corresponds to when we were going through the quarantine period with COVID. And so it's a good example of a site that was definitely impacted by COVID. For our gas flares, we do the same sort of thing. And so here's the shortwave infrared radiant emissions, the temperature, and then methane equivalents. So we basically index the heat output to the methane that it would take to generate that much heat. Okay, well, that's my presentation. So perhaps we have a few minutes for questions.
Oh,
Okay.
thank you. We're going to hear up for Erinn. Erinn's here from Alliant Energy.
All right. Good morning. So my name is Erinn Monroe-Nye. I am a regulatory relations and policy consultant with Alliant Energy. So I'm like a utility person smashed in between two scientists. But I can talk a little bit about some of the practical applications and things like that and the data needs for energy efficiency. So a little bit about me. I am a EAP alum. I graduated in 2005, so I was 20 years out, still have a career. And actually it's been phenomenal. And I've actually been lucky because the last like 20 years in the energy industry has been just incredible change. And it's been very exciting. And I've been involved in a lot of really amazing projects. So right out of college, I gravitated towards energy efficiency because energy efficiency solves so many problems, environmental problems, there's some social justice problems, comfort in your home. I'm a person who's always cold. So, and actually I grew up in a farmhouse that didn't have good insulation. So like every morning we would race down and sit in front of the space heater. And so that was my experience growing up. And so energy efficiency has just always been something that I've been very, very interested in. And prior to coming to Alliant, I was actually the director of Wisconsin's Focus on Energy program, which is a statewide program here in Wisconsin that offers technical assistance, rebates, education and training to try to promote energy efficiency in the state and help customers implement energy efficiency projects. And so I just love the presentation that I just saw because one of the biggest, Wisconsin's a highly industrial state. And when I worked at the Focus program, we worked with a lot of foundries, paper mills. Paper mills are huge consumers of energy. And so we really got to, so having information like this to be able to sort of like pinpoint and identify the big waste heat emitters in the state is really, really incredible, really valuable. So I didn't put together a lot of slides because mostly I just like to talk. But I did want to kind of tee up when you're running, an energy efficiency program, you have a lot of information that you don't know. So identifying opportunities, are there particular locations that we should be focused on? So for example, areas with high energy burdens. And so at Alliant, we've been really digging in on our data and kind of overlapping other data sources to try to determine where are the areas where people are really struggling and that energy burden can be very high. And what can we do to help those customers? What kind of programs can we put in place to try to make it easier for them? So that's a very important thing. Also, poor building stock. And a lot of times not always, but a lot of times those things do sort of go hand in hand. You will find poor housing conditions and areas with high energy burden, they sort of go hand in hand. And areas that are more vulnerable to environmental concerns and being able to see what we can do to sort of alleviate that as well. Are there, specific customers? So we're just talking about this unexpectedly high energy intensity. Is there something happening at a home or a business that is just wrong? And then we also want to be able to, so that helps us sort of identify where the opportunities are. So let's say we've identified a paper mill. What we need to do then is deploy somebody there to look at what's going on and to really assess having good data on what's going on in the facility, having, some engineers go out there, take a look at things, do some analysis, can help identify improvements. And so after that, we want to be able to measure the impacts of those programmatic interventions. And can we quantify how much energy was saved, associated emissions reductions, all of that. So kind of measuring the after impacts of your interventions. You want to know you're doing something, right? You want to have an impact. So there's been this progression, and this is, I think we had that historical look back at satellite data, and I thought something sort of analogous in the utility sector might be meter data and how we have been able to really progress. So when I was a kid, we had a meter reader that would come to your house every month and read your meter, and that was your data. That was your thing. You had a bill, and they might not even come. There might have been a holiday, and so they actually came a couple days later because of scheduling. And so you didn't always have an actual month of data to look at. So really your bill, it came, you paid it, you weren't really paying it, that much attention to it. And then about 20 years ago, or in the early 2000s-ish, we started to see incredible advancements in metering infrastructure. So advanced metering infrastructure. And now you've got meters that are taking measurements, every 15 minutes. Now that's data. That's actually something you can do something with. And we use it quite a bit. A couple examples, what we have learned is that you can look at that and then put weather data, or if there's publicly available data on building characteristics, such as like how old a building is, when was it built, you can start to pull apart and disaggregate the different end uses that are happening at that site. And so there's, and it's challenging, but you can look at like a laundromat is going to use energy in a different way than a restaurant. And you can kind of look at the data over time and say, this commercial office building, they're leaving their air conditioning on Sundays when nobody's there. And we can do that from afar, and kind of, it's sort of like a remote sort of commissioning or retro commissioning of a building, being able to identify waste like that with meter usage data. The challenge with it, there are some challenges. One is that data is actually private. It belongs to the customer. This is not something that we can put gigantic data sets out there and say, okay, everybody have at it, if you're a scientist. So it can be a challenge if you're a unit of local government or state government and you want to kind of look bigger picture. Getting that utility data, that can be a challenge. It is private data that belongs to those customers, and we can't just put that out there without their permission. Now, some customers are very happy to have someone look at their energy data and help them save energy, but that can be a little bit of a challenge. So that's where this emerging idea of using, these Earth observations and the satellite data really can marry up really nicely with some of the advancements that we've made in meter data. So a couple things, you can look across broad swaths of territory. You're not necessarily constrained by a utility, territory. So if you are wanting to look beyond that, that's really helpful. It's available to all. We just have to get more people learning how to use it and have it just kind of more broadly used. So I think being able to marry these two things up in the future is going to bring tremendous opportunities to, helping us address energy demand and what we can be doing to help our customers. So I think it's super exciting. I'm thrilled to be here and to learn more about what's going on in this space. But I think this is sort of like the next frontier. I think this is in the utility space. This is sort of taking it beyond, our excellent meter upgrades to being able to take it even further. So we're waiting for questions till the end. So
We are.
okay.
We are. Thank you, Erinn.
Mhm.
Dr. Pachauri next. I'm going to do an informal kind of field question. How many of you know how many steps you take a day? Ish. Right? Is it a metric you used to? How many people know how many kilowatt hours they use? Okay. I would expect a little more in this audience, so I'm a little bit surprised. But I think that's one of those metrics that we don't usually talk about. We don't talk about that to each other. I can say I took 10,000 steps a day. People lost some context what that is. If I say, how many kilowatt hours I use a day, you're like, oh, I don't know if that's good or bad. So this ability to talk about energy in a really meaningful way. I'm sorry. Go ahead. I'll stop talking.
So yeah, hello everyone. My name is Shonali Pachauri. I work with the International Institute for Applied Systems Analysis, way out in Austria, just outside of Vienna. And I'm really delighted to be here for several reasons. One being that there's been a very long association between the Energy Analysis and Policy Group here in Wisconsin and EASA, and a lot of exchange of scientists across these two institutions over time. And just as of this year, this association has been cemented further through a generous contribution by Wes Fole, who's been someone who's been very active in the Wisconsin, at the University of Wisconsin, Madison, and also has spent time at IIASA. And so, we've had students from EAP come spend summer programs at IIASA, and we've had scientists come back and forth. And it's so really exciting for me to be here at this point, at this juncture. I'm really also very honored to follow in this conversation that Chris started, and then Erinn has also contributed to just before me. So some of the data products that Chris mentioned are data products that I've worked with colleagues, and Erinn kind of focused on this high energy intensity demand areas, and I'll be talking a lot about low energy intensity demand or no energy demand areas. So I think it's a really nice progression in that sense. I just want to sort of put it out there right up front that I am not a GIS person. I have no background in geography or geographic sciences, but I've had the privilege of working with really bright people who work in this area. And that's how I've done the work that I'll be presenting today. And this is very collaborative research that I've done with several different people. So I started working with people who work with satellite data over a decade ago, actually. And this is very early work where we basically tried to look at satellite night lights data to look at electricity access around the globe. And what we did was really try to have a special focus on the spatial dimensions of unlit rural areas across the globe. And what was really striking to us was that in areas where you lack access to electricity, there are vast differences in how densely population is distributed. And so particularly in sub-Saharan Africa, you have very sparsely populated areas without light. Whereas in many parts of Asia, you have very highly densely populated areas that didn't have light. And as I'm talking about now, they do have light, but this is over a decade ago of work. And this was quite illuminating to us because, of course, then when you think about solutions for electrifying these populations, it's going to be very, very different. And so there was already back then this vast and deep discussion on should you be going for decentralized or centralized grid extension for electrifying these populations. And of course, that conversation has really accelerated over time in the last decade or so. So, this is just very early work that I did with some colleagues. This is the most recent work that I've done with colleagues at IIASA, where basically we've looked at looking at sort of unlit areas, so focusing very much on regions of the world where there's no light, but there's habitat. So so where there's global settlements, you have global settlements, but they're unlit. And basically what we saw was that when we combined this satellite nightlight data with the world settlement footprint data, then you can see that in 2015, for example, almost 20% of settled area had no detectable light at night, right? So, and that corresponds fairly well with other estimates out there in terms of the percentage of population globally that does not have light, right? So this was quite interesting for us, and we did this, for different countries of the world, and we split it by rural and urban population, and we really found that there was a good resonance with other data sets that were out there that kind of gave us estimates of populations that don't have electricity. But then we kind of went one step beyond that, and we really wanted to try to see, okay, can we really see if these unlit areas help us to get at estimates of poverty and whether it correlates with other data that shows wealth index at a household level. So we combined, we kind of validated the information that we got from the nightlights unlit data with demographic and health survey data. Demographic and health survey data, these are surveys that are done across mostly the global south, and they're basically to assess development, different types of development. And again, we saw that for like African countries, we saw that there was really a clear association between increasing percentages of population or communities that were unlit and decreasing economic well-being. So there was a really good cross-match in terms of populations that are unlit and those that have very low economic well-being. And this was particularly true if you split it out rural and urban and look specifically at rural areas where we found that this association was really high. And so what we tried to do was kind of for different countries of the world, especially those in sub-Saharan Africa and South and Southeast Asia, but also parts of Latin America and South America, we tried to map the wealth class of geolocated households in these unlit areas. And we found that the accuracy of doing that was quite high. It was like as high as 87%. So again, like a really good match in terms of being able to associate the unlit settlements with economic well-being. So another important piece of work that we've done recently is being to try to track, again, electricity access and energy poverty in sub-Saharan Africa. And what we did in this work was try to go beyond just this binary distinction between lit and unlit areas, because of course, that's something that a lot of people have done. And we've seen, of course, that you can get a pretty good accuracy in terms of determining where are populations without access to electricity. And that was something that, of course, we wanted to build on further. So what we try to do is really look at not just people who have access to electricity versus those that don't have access to electricity, but then go beyond that and look at tiers of access to electricity. So distinguishing between less access to electricity and more access to electricity, combining it with sort of the extent of light radiance that you could get from satellite data. And so our approach was to really create this open source data that would allow people to track electricity access and to do this at as fine a resolution as we could, given the data that was available, and to look at this over a period of time. And we coincided the time period with the Sustainable Development Goal time period. So the Sustainable Development Goals started in 2015, and we wanted to look at the first 5 years of achievement over that period. And again, we distinguish between rural and urban areas and try to do this at the province level for sub-Saharan Africa. And so again, as in terms of the data inputs, we use the nightlight data. We've used the global settlement data. We looked at urban and rural classifications, and then we looked at data that looks at administrative distinctions by province. And again, we tried to validate what we found in terms of the analysis with DHS data or other survey-based data like the World Bank's Living Standard Measurement surveys. And so we created this output data set, which then gives you the number of people without access over the period from 2014 to 2019. And then, as I said, not just access to data, yes, no, not just binary, but really determining the access by tiers. So less access, more access. And this data is openly available. It's hosted on our website. And we have a dynamic data visualization interface that you can go and really zoom into specific spots to try to get a better sense of what's happening in these different regions and how it's changed over time. Then taking the data set that we had, we tried to do further analysis to try and get an assessment of how has progress of electrification improved over time over this period in sub-Saharan Africa, and then also by these different tiers of access to electricity. And what we found is that we saw huge inequality actually in how access to electricity has improved over time in sub-Saharan Africa. So there are large parts of Africa that have no electricity, still, we know that, particularly rural parts of Africa. But we also found that there's a strong, again, correlation between electricity provision, these tiers of electricity access, as I mentioned to you, and wealth inequality or income inequality. So provinces or regions with higher income inequality also tended to be less electrified. So that was kind of an interesting insight that we got from the analysis. And then we did another set of analysis where we really tried to identify hotspots. And what we did in trying to identify these hotspots were not just looking at areas where you had no access to electricity. That's of course clearly one kind of hotspot that you can identify. So we looked at between 2014 and 2019, where were there regions in sub-Saharan Africa where population increased very rapidly, but you didn't see a concomitant increase in lit area, right? So that was one kind of hotspot that we tried to identify. But then we tried to identify also within lit areas where you saw, like in particularly urban areas, where you saw big population density increase, but then again, not a concomitant increase in the lit intensity. So I tried to identify these different kinds of hotspots of the areas where, you had high potential latent electricity demand, and that was demand that was not being met. And so, really interesting insights from some of that work that we tried to do for Africa. And then I know I'm coming to the end of my talk, but I just wanted to kind of highlight two additional areas of work that we are now doing. This is work in progress, so I don't have final results to share with you, but I just wanted to highlight this because hopefully this is something that will be published soon. Again, one on my right, your left, is a map of sub-Saharan Africa, where we're really trying to look at the potential for solar irrigation in Africa. So, I mean, there's been a lot of focus on providing electricity access to homes. And of course, that's essential. That's the first step to getting some development happening in parts of the world that are dark. But you also need to have electricity for productive purposes. And food security is one of the most essential challenges that many parts of sub-Saharan Africa is facing. And so there's a lot of interest in how can we expand irrigated farming in sub-Saharan Africa. So at the moment, most of the farming in sub-Saharan Africa is rain-fed. It's not irrigated. There's no electricity access. So we really need to expand access to electricity on farms in sub-Saharan Africa. And this is one piece of work that we're doing, where we're really trying to look at not just solar irradiance and farm data on the ground, but also then looking at the benefits of providing the solar irrigation in terms of increased agricultural productivity, food security for the region, and so on. And then on the other side, you see work that's being done by another student who was spending the summer at IIASA last year, where he's trying to look at the global solar rooftop potential. So we saw in the first session how this was done at a very local scale for somewhere in the US, but this is a global work where trying to look at the potential for solar rooftop globally. And again, combining information on solar irradiance, but then also settlements, global settlements, and looking at the LCOE, so the levelized cost of energy across the globe, to really look at the potential. So interestingly, you would think, oh, Africa's the place to do it, but actually maybe not, because firstly, there's not much built settlement in Africa. And then also in terms of the LCOE, it works out that parts of Asia might be better suited to some of that global solar rooftop. So I'm not going to try and conclude the talk, but I just wanted to leave you with a few key takeaways. One being that Earth observation data is really critical and can be very, very important to complementing other data sources, particularly in regions where you don't have good access to data or where you don't have regular surveys happening for doing, sustainable development goal monitoring and tracking. And I think it's really important to use satellite data where you can to help reveal the heterogeneity, because you can do grid level information gap, you can assess data at a grid level and really get at the heterogeneities and the inequalities and the inequities in terms of distributions at subnational scales. And of course, where you have higher resolution satellite data, whether that's temporal or spatial or both, it can really be used to create more than just binary indicators of electricity access. You can really get at, tiers of, you can look at the luminosity and you can get at tiers of electricity demand. You can get some information on the reliability of electricity, which I think we're going to hear more about later. And so, yeah, it's extremely useful in that. So I'll leave it at that. Thank you very much.
All right, so we have our questions ready. Is there any way we can shut the light off so we can have our panelists up here without?
Yeah, I
being
think
blinded?
so. I'll work on that.
Yeah, I'll just pull up another chair. Would you mind? if it's- The microphone be able to pick us up?
Yes, I believe so.
All right, this is being recorded, so, let's see.
There we
You can speak loudly or you'll repeat your question, so our online audience members can have it. Yes. You mind standing up?
Yeah.
Make it even more awkward.
I don't know whether I'm all. So this is like a question from all three presentations. So I have two doubts, and I really am not your cooking person or a GIS person. So I just want to figure out, is there a way that we can do two things like efficiency and reliability is something that comes to my mind. So first is we keep measuring night lights, but is there an efficient level of night light? As in, if it's more bright, does it mean that it's more developed or say it's the right thing to do? So is there a way that we can measure that the brightness in one area is most efficient? Any higher than this would be a waste of energy? Is my first question. And the second is there a way that we can find that and this is actually especially coming from Shonali's presentation, if there are instances which have low levels of energy that we or say electricity that we can see, but is there a way to measure the reliability of that, whatever is available right now? Because we have temporal data as well, right? So can we do that? And instead of trying to give them more energy, just make the existing energy more reliable to that area? That's it.
Yeah, well, regarding the efficiency of lighting, there is something that can be examined in addition to the average radiance. We're now producing products where we generate the other three moments: variance, skew, and kurtosis. And so one of the things that we find is that the brighter the lights get, at least with our traditional technologies, the higher the variance. And and what we also find is that in the developing world, that there are fewer bright lights. I think it makes sense because they are not expending their resources on lighting that may be superfluous to what they need to accomplish. So that's one area that can be examined for evidence of efficient lighting. And one of the things that we found in our examination of the average brightness versus variance is that there is something that we can define as core lighting, where the variance is constrained and the brightness is relatively dim. It's not terribly bright. And there is on that scattergram, you can actually see a vertical column that is the core lighting that contains 96% of all the grid cells that we examined. The other thing about the low detection limit is that when the lights are already dim, you've got less signal to work with in terms of the lights. And what you will often see as an indicator of some instability in the power supply is that the radiance drops to the noise floor. And it can do that over and over again. And so that's an indication that the lighting there has some instability.
Yeah, so on the question of efficiency, I mean, you've already heard a really good response to that, but I think it's really, one needs to look spatially at, of course, the lit, unlit data, but then also population density and human activity, because it's all very correlated with that. And just the data set that Chris presented, where you can see where you have industrial flares, industrial waste burning, or gas plants, power plants, and so on. That kind of information, if you had that kind of information and combine that, I think then you could start to tease out, are these areas where the very bright lights have anything to do with efficiency or not, right? And then as far as the question of reliability is concerned, I think you're going to hear a talk later in the afternoon today, where really they've used this data to try to look at the outages that have happened, and that you can again very clearly detect, as Chris mentioned, and does help to get a sense of where you have the power infrastructure, but it's weak, and that you could really try to provide better access to people without necessarily increasing supply, but just improving it. Yeah.
I mean, one thing I could maybe add is that, but this would be in areas where you have like aging infrastructure, the type of lighting and the way that it looks would be different, right? Like if you're using a high pressure sodium light source, that's going to be a very kind of yellowish, orangish light versus like an LED source. And the LED source also can be a little bit more directed toward the surface. It's going to have a little bit less, what do they call it? It's going to splash outside of the footprint a little bit less. So, I mean, that's would be another interesting thing to look at.
This is a question that's addressed to Erinn. So I thought that this meter data archive, that's just a phenomenal asset. And I think the same thing happens with public health data. And there is protocols, could you aggregate that, like at the census tract and provide the same kind of information that you have in terms of housing, housing characteristics, things, and energy consumption, because that would be just an invaluable data set to really start tying, more tightly to the satellite data.
Yeah, I love that idea. And I will say when I was working at the focus program, as we were trying to assess energy burden, one of the parallels that we kept coming back to was public health, right? The social vulnerability index and all of these things. There's a lot of correlations there. Yeah, and aggregating the data up to something like that, I think there's potential there. I think that we're going to get into like implementation technical challenges, right? Are all the data sets going to be able to be warehoused someplace? But I mean, my boss is here. But I think that is something that would be, I mean, it would be a great thing to be able to do, to kind of, aggregate that and make that data, anonymize it and make something available. I think there will be, that would be a great thing to be able to do.
It would be great to demonstrate this, kind of as a pilot from Wisconsin, the Wisconsin idea. There is there's a data science institute that does that kind of work. We work with the day-night band, and that might be something to think about.
Yeah, that would be great. I'd love to connect with you.
My question is for Dr. Pachauri. You had briefly mentioned productive loads and trying to quantify it with imagery. And I was wondering what other aspects of productive loads, aside from, say, irrigation, one could lend imagery to, given that energy intensity or energy usage is heavily correlated with development so that we could start to make those.
Yeah, that's a good question, and that's something we've been thinking a little bit more about, actually. So one of the things that we are already thinking about and exploring is, it's kind of related a bit to the irrigation, solar irrigation potential. Of course, in parts of sub-Saharan Africa and South and Southeast Asia, there is no cooling availability, whether it's for food transport or vaccine transport for that matter. And there's a huge demand for cooling and refrigeration, for also reducing food waste. And there again, I mean, I think some of the satellite Earth observation data sets can help to identify, farm areas and then areas that are lit, unlit, where there is electric infrastructure and there isn't, or where there isn't. And I think that can be one additional area where one could expand analysis to really understand the potential for cooling. And then other work that we try to do again is, some of these areas that we've identified as being hotspot areas of latent electricity demand are also highly correlated with areas that are most vulnerable to climate change and to extreme heat events. And so again, you would expect that cooling demand is going to really rise in these areas, and they have no infrastructure to meet that demand. So I mean, I think that kind of analysis is another area that one could expand.
I'm gonna go to the back, and then I'll come back up front.
Hi. So I've been curious, a lot of people have been talking recently about light pollution and its different effects on the world around us, from dimming out the stars to its effects on local wildlife, bats and migratory birds. And ostensibly some of the light that does contribute to light pollution would be detectable by satellites. So what I was wondering is, in the event that people, maybe small groups or even large groups of people, take steps to mitigate the light pollution that they or their activities produce, how that might affect how you all collect your data.
It won't affect how we collect the data. NASA and NOAA collect the data for us, but it could propagate into our products. And where you might see it is that in the nighttime lights products, we're trying to find all the light that we can that's coming from the Earth. And that includes the glow around bright sources. And so we don't exclude that. We do make a higher level product where we try to trim it off, because we don't think there's actually a light source there. It's just bleeding over from other areas through the scatter in the atmosphere. But that's if there were more efficient lighting, and if some of these efforts to reduce light pollution were successful, that's where you might see it. And it's very dim, but it's very spatially extensive, and you can easily distinguish it from the light from city centers where you've got an actual light source. So that's where I would look for it. I haven't seen any yet, but maybe we will someday. And that's one of the reasons we curate our products, so that you can look back in time and examine that.
Yes.
The first is just an observation about the satellites and light. It was I think a recent article in The Economist last week or two talking about identifying authoritarian regimes' claims of GDP growth versus actual, and they were using satellite night light imagery to tell them to indicate, to show that they were off by about 50%, like they were lying by 50% on GDP growth in these authoritarian regimes. So information point for you. The next question for Erinn is, have property managers or consultants working with their owners of buildings they design requested data on energy use from buildings?
From me personally, no, but from the companies, I would imagine that yes, I would imagine that they have, but I have not been, I don't work in the actual data group that would take that in, but like our account managers, I know have access to all the usage data and work with the customers to help them understand it. The focus program also does that, provided the utility or provided the customer will allow access to it.
It
to
would be
do-
interesting
yeah.
to know if designers and leaders are looking at their energy status.
Yeah, I mean, I would, yes, they are. I can say that they are, definitively. Depends on the business, but a lot of them, some of the more large users, they have like an energy manager on site, that's their job, right? Is to kind of keep an eye on how their facility is operating. And so that energy usage data is critical for that. And like I said, our account managers work closely with our large customers to help them understand. I think where the gap probably shows up more is in small to mid-size businesses, especially because they don't have personnel dedicated to that. And a lot of times, a small business owner, their energy bill is not their biggest concern. They're running a business. And so I think that's where the real challenge is, if we can get to those customers a little bit more and help them.
I think the challenge is broader than that, but thanks for responding. I work with energy efficiency in a lot of buildings. And I don't see the same interest in feedback on design of buildings or property managers asking about the design of or just the operation of their buildings as a rule of thumb.
Yeah.
This is a question for Shonali. So I think you showed us the data for global access to electricity from 2015, I believe. My questions were, how often is this data updated? And have you seen a temporal trend in increase, like some sort of an increase in access to electricity as the years go by? And have you done some sort of an uncertainty analysis in the numbers that you're showing? Like what is the uncertainty associated with the numbers that are presented in your products?
Yeah, so the data I showed for sub-Saharan Africa is 2015 or 2014 to 2019, actually. And in sub-Saharan Africa, approximately 115 million people got access to electricity over that period. So a significant improvement in access to electricity. But then if you start breaking it down by how much electricity and looking at the luminosity to see tiers of access to electricity, what we found was that in fact, people got connections, but not much electricity, to be honest. So that's where having more than just the binary information on is it a lit area or an unlit area is really useful to get at is the electricity access benefiting people, which is what we are wanting to try and get at. And of course, there is uncertainty associated with all the analysis that's been done. I wouldn't be able to tell you offhand what that level of uncertainty is, but if you go into the data, you can go look at the paper. It's all documented in there.
My question is for Erinn. What is your take on prepaid electricity programs for those that experience high energy burdens, and does Alliant Energy have any programs that are prepaid?
Like a prepay
Yeah,
program?
you purchase energy credits before you use them.
We don't have a program like that, but we do have other programs that customers can use. We do have a fixed bill, so we'll look at what their usage has been and then try to assess what we would expect, and then they can get a kind of a flat bill. But actually, one of the more interesting things, and this is sort of, I wish my colleague Harvey Dorn was here, because so I think we have a residential demand rate, which basically tiers your bill based on how much you're drawing from the system at any time. So like what really holds costs down, or what really costs a lot in the energy industry, are these spikes in demand, because you have to build the system to be able to accommodate these very high spikes in demand, and that is a huge driver of the cost of energy. There's been some discussion that if you brought in like a demand charge into a low income, and generally you see this more on businesses. You generally don't see a demand being a component of a residential bill. But when we analyzed our customers' usage, we actually found out that a lot of lower income people would actually benefit by going on a demand-based residential rate, because you weren't seeing the big high spikes there. So when we looked at that, so we were actually trying to communicate to our customers a better way for them to understand like how the different rates that are available to them benefit them. And that's actually one, I think that's kind of goes against the conventional wisdom that if you did that, it would be more expensive for those customers. But in actually looking at the data, that's not what the data says. And so we've been trying to get our customers onto to better rates. I mean, that rate design is actually a huge component of it as well. And that's going to be, I mean, I could go on if that's okay, but that's going to be a really interesting thing going forward too, because if we're generating more of our electricity from solar, we have then more availability of electricity during the day, which has traditionally been a more expensive, time when we would try to curtail usage. We'd say, maybe don't use it, in the middle of August at 3 o'clock in the afternoon. But now we in aggregate are going to have a lot more solar energy available at that time. So you might start seeing time of use rates changing to encourage people to charge their cars or use their energy intensive devices maybe during the day when the sun is out, and then less so at night. Over time, this will happen. I'm not saying immediately, but over time, there's going to be, and it's that changes. I mean, that changes consumer behavior. If we think about what it means, people turn their lights on and they expect them to just go on. We're talking about changing behavior of a commodity that people don't even necessarily understand that they're consuming, to be able to kind of tailor it and fit it to what generation is going to look like in the future. And so anyway, it's fascinating. But rate design, and we do have also programs to help customers buy down the costs of doing insulation and air sealing in their homes as well. So it was a really long answer.
So you need to know your kilowatt hours and when you're using them.
Yeah.
I have two questions related. The first one for Chris is, do you detect LED usage, and has that changed in the last few years as that's been implemented? And the second one's for Erinn about Nest thermostats and smart homes.
Oh, well, Beers is a little bit disadvantaged for discriminating lighting types because it's a single panchromatic band that includes the near infrared and part of the visible. And so if you had, say, 3 or 4 spectral bands, you could distinguish LEDs from high pressure sodium and from metal halide. We don't have that. But there are some clues. The best clue that we found is in the variance. And we did a study in Tucson where the city replaced all of their high pressure sodium streetlights with LED streetlights. And the LEDs have almost no flicker. And the day-night band pixel collection time is between 2 and 3 milliseconds. And at 120 hertz, well, that's about 8 milliseconds. So the high pressure sodium and metal halide lights are flickering 120 times a second. So about 8 millisecond cycle. And the day-night band pixel aggregation time is short enough that it, unbeknownst to us, is picking up variance that's due to flicker. And so when you change to LEDs, what are the consequences is there's less variance in the signal. Yeah, so we've got a nice paper on that.
And my question was just like, have you noticed a change or how does the sort of the Nest and the kind of smart house thermostat affect what you're looking at?
I think there's such a huge opportunity there with demand response for, and that is something that Alliant's really interested in as well. We're we have programs to kind of help, basically what demand response is when the utility is starting to, as more usage is sort of coming online, people are waking up, turning their lights on, getting things going. And the energy use starts to increase, and then you're turning on your generating units kind of as that goes up. And it's getting more and more expensive. This is sort of how it goes. And then what you can do is you can signal, hey, folks, let's turn it all down a little bit. And you can see this like flattening of demand. I mean, this is what kept California going just a few weeks ago when it got so hot there, right? Is they sent out a text message to people and they said, reduce your energy use. And it did, and it kept the grid stable. So I think that's one of the interesting things about these communicating devices and these smart devices is that you can send a signal out and you can say, okay, let's let our houses warm up to 72 degrees instead of 68 degrees. And it can really provide a lot of benefit there. So demand response, I think, for those devices, the energy efficiency side of it, I mean, we promoted them for focus, and I do think there are efficiencies to be had. However, you are enabling someone to turn their air conditioner on when they're on the way home from someplace else. And so I do kind of wonder, I'd love to see, more, and there is some kind of emerging research on how, human behavior is actually kind of, they're supposed to be smart. They're supposed to learn your behavior and respond to it, but you can also like control it yourself. And so, but yeah, I think there's a lot of all of these connected devices are going to have great capabilities for demand response and for, keeping the grid stable.
We're nearing lunchtime. We have time for another question or two.
Thank you. Thank you for your wonderful presentations. My name is Parthendu Pandey, and I am a lead urban data scientist at Winston. My question is to the panel about, I heard a lot of interest in new data and use of data in understanding these challenges. So how do you, and as a data scientist myself, I'm just wondering, how do you view the next transformative advance that's going to come from looking at these data sets? And so how do you identify where that's going to come from? So if you reflect on that. Thank you.
That's a big question. Yeah, but I think I could take a crack at maybe starting us off on that. So I think part of this was responded to already in the first session this morning, where when you have more temporal and spatial resolution to this data, then that of course really allows you to do a lot more in terms of the analysis as well. And I think that's going to be one frontier where we can really do a lot more in terms of analyzing how things have changed over time or how spatial patterns vary and combine. And I think also the other area where I think there's a huge frontier is combining different data sets. So layering one upon the other, like we've tried to start doing some of the analysis that we're undertaking, where then you can really combine, okay, this is night lights, this is settlement, this is population density, this is urban and rural, this is urban size settlements, activity patterns, and so on. And then you really start being able to tease out, what's influencing what and where the drivers are. And I think that's another really interesting area of research that we're starting to see happen. But yeah, I'm sure the others will have a lot to add.
Oh, I was going to say that the same point that you mentioned, that we're really just scratching the surface in terms of integrating data sources to do more complex analyses. So I think there's a lot of potential there.
Can I go with the student for the last question? All right, go ahead.
This is a question for Shonali. Going back to your observation about sub-Saharan Africa, people do get access to grids, but they end up not getting electricity. So do you think that's a trend because of a demand supply lag, or that the cost of energy is too high, and do you see a pattern across developing countries? So do you see this in sub-Saharan Africa and then Southeast Asia or East Asia? Thank you.
Yeah, that's again a big question with a big answer. So it really depends, because there are huge issues of affordability and reliability of access. And that, of course, plays into how much people who get connected are able to benefit from the electricity. And particularly, I think in many parts of the global south broadly, we find that it's not so much the fact that the cost of electricity is that high, but it's the connection to electricity, that the upfront cost that becomes a big barrier for people. So it's the connection, the initial connection to the grid or to the decentralized option that you have in that area. Plus, people don't have that cash flow, regular cash flow that allows them to invest in appliances. Again, that's an upfront cost. That's a big barrier to people. So you need to have business models that allow people to stretch out the upfront cost into a sort of smaller regular stream of payments. And that's happening in some places, but it's not happening everywhere. And that, I think, is a big issue in many parts.
You've been amazing. Can we give a round for our panel?